I'm Jim Westberg. I'm in charge of North American sales for Solidscape. I've been with the company about 7 years now, involved mainly in the jewelry market. I probably will start off by saying jewelry still is probably 70% of Solidscape's sales. It's the largest vertical market. We do sell machines in the medical industry, orthopedic, artificial knees, hips, spinal implants, a lot of research applications in big universities that need precision and accuracy. Some general industrial, some of the Fortune 500 companies, maybe prototyping cell phones or whatever the widget may be, aircraft engine blades for companies like Pratt & Whitney and General Electric. Again, the commonality there with jewelry is the ability to directly investment cast the models. What I wanted to do is give you a little overview of the company. It's not that old of a company. We were founded in 1994. It's a privately held company up in Merrimack, New Hampshire, which is only about an hour north of Boston. It's about 5 miles over the Massachusetts border. This is a bit dated now. We're up to about 2,500 machines worldwide, and as I said, probably 70% of those are in the jewelry industry. Both domestically and internationally. The percentage of sales in North America is probably about 40% of our sales in North America, and 60% is throughout the rest of the world. Some of this presentation doesn't have much to do with jewelry, so I'm going to skip over those parts of it. We are currently offering 2 machines that are geared to the jewelry industry. The one over here on the table is the T66 benchtop. The BT stands for benchtop 2. And then about 6 months ago, we came out with a machine called the R66. The R basically stands for the custom retail type jeweler. And we'll go into the differences. We also have a larger machine that's got a 12-inch by 6-inch bed, build plate. That we sell mainly to industrial companies doing bigger parts. There are some jewelers, I'm not exactly sure why, because in my opinion there's no benefit to a jeweler, but internationally there's a few jewelers that buy this 12-inch by 6-inch bed. These 2 machines have a 6 by 6-inch bed. When we go over to the machine, you'll see that. I'm going to try to, gets a little technical. I'm not going to put you to sleep, but I'm going to try to tell you what's important to a jeweler. This machine is capable of going from layers that are as fine as 1/2,1000th of an inch to as coarse as 3/1000ths of an inch, and there's like 5 settings throughout that range. What that means to a jeweler is surface finish. I mean, jewelers call them all different kinds of things. They get their loop out and they look and they see, oh, I see the grow lines, or I see the step lines, and those are almost the little stair steps. And of course, the finer the layer thickness, the less stair stepping you're going to see, and that's why this is important with jewelry. It's by far and away finer layers than any other machine that anybody's trying to sell into the jewelry industry can do. The neat thing is that the operator can select that. Most jewelers run either the finest resolution, like a custom retailer, if you're doing one-off type pieces, you're going to want to get the best possible surface finish you can. So a retail jeweler doing a one-off may run the machine at its finest resolution, where a higher volume manufacturer who's got more bench jewelers or whatever may run it at 1 or 1/2,000ths of an inch. So there's really 3 resolutions that most jewelry customers will run at. It's conceivable if the boss just wanted a crude, fast prototype, you may run a piece at 3/1000ths of an inch. You're not going to do anything. Maybe the boss just wants to see what it looks like real quick. But typically it's not used in an actual manufacturing or production type basis. The machine is very accurate. Again, it's an engineering spec. Engineers love this stuff, but the machine is got an accuracy what's called plus or minus 1/1000th of an inch per inch, which means if you had a 1-inch cubed, we will basically guarantee that thing is going to be within 1/1000th of an inch of however you designed it, or about a 0.025 millimeters. Where's that? Why is that important to a jeweler? It can be fit of stones, prongs, all the dimensions that are critical. This is one of the it is the most accurate rapid prototyping machine in the world. But it's slower than some of our competitors, and I should have mentioned up here, when the manufacturing manager or the RP or the model making design group or whatever, the trade-offs they have is the finer the resolution. Like if you ran it at a 1/1000th of an inch, you're going to get the longest build time, because it makes sense, there's more layers. I mean, there may be 1,000 layers in a piece of jewelry. If you built it at a 1/1000th, you know, it could be 2,000 layers. So it's going to take the machine longer to print. I'm not going to get some of our. There's one or two competitors that are trying to sell machines into the jewelry industry. The reason they don't spec their stuff the same way we do, they use droplets per inch. That's how many drops our jets that I'm going to talk about are actually squirting out the material in a square inch basis. And our machine is putting down about 5,000 droplets per inch in the X and Y axis and 8,000 droplets per inch in the Z axis. To put it in perspective, these competitive machines are only putting down about 500 to 800, so it's about 1/10 of what our machine's doing. The only reason, one of the only reasons we succeed in the jewelry industry is the ability to directly investment cast these models basically without doing anything special at all. There's a couple other machines that are being sold into jewelry that are resin-based, plastic polymer type models that you just do not get a clean burnout, unless there have been guys that have figured it out, but it takes them a couple of years. They have to buy special casting equipment. They have to do special burnout cycles and procedures. What we pride ourselves on is you can actually take a hand-carved wax, tree it, and sprue it on the same tree with our models, use the same procedures you are today, and the material's going to cast fine. There's one exception that people have to mess with a little bit or experiment with a little bit, and that sometimes is platinum casting. There's a couple little tricks. Some of our customers dip our models in like a mineral oil to kind of slow down the acid content, the platinum investment from attacking the model too quickly before. But usually it takes like a week's worth of experimentation and customers perfect what they have to do. And we probably have 100 customers now in the United States that are 100% platinum. And you know, they have to mess with it the first couple of days, then they nail it, they have the recipe, and 5 years later they have no problems casting material. Everything in the machine is non-toxic, non-hazardous. We use a proprietary thermoplastic material. We have patents on it. We feel very strongly about it because of our position in the jewelry industry. We did patent this material so nobody else can use it. As I said, it burns out beautifully, no ash, no residue. The machine also comes with a monitor and a keyboard, which the monitor basically gives the human interface to the machine, and we'll talk a little more about that as we go along. It's very user-friendly, but it provides some diagnostic information, not only about the exact job that's going on now, but the temperatures. It's a very temperature-driven process, and all that kind of information is displayed if the operator ever needs it. Technically, this is called a drop-on-demand jetting process, which we also have patents on. But essentially, what's happening is we take a granular material. The green is actually the build material, and the purple is what we call a dissolvable support structure. And I'll talk about that a bit more. But this material goes into hoppers in the machine, down into tanks, and it gets melted, and then pumped up through heated lines down to these little jets that are the heart and soul of the machine, and they're spitting out these very precise droplets. And so essentially, a lot of people get confused between milling machines and this type of technology. Milling is, I'm sure maybe you're using them in your shops today, they cut material, they're subtractive. This is additive. You start with nothing and you build it up layer by layer by layer. Hence the term drop-on-demand jetting. We are able to precisely control what we call the Z-axis thickness. I'm going to show you that we have a cutter inside the machine, and at the end of every layer, the material cools for a few seconds, and then a cutter sweeps across the bed. When the material comes out and it's molten from the jets, if you magnify it, it's a little bumpy. So after it cools, we come across and we shave the top of those little bumps off to make a really nice smooth surface, and then it starts printing its next layer again. It's pretty amazing. You can't see it with a naked eye, obviously, but one of the jets is actually putting down 6,000 droplets a second, and the other jet puts down 12,000 droplets a second, and these droplets are about 3/1000ths of an inch in diameter. This kind of grossly shows the difference in some of the technologies and the stair stepping. I mean, imagine if this was the shank of a ring, for instance, you know, you're trying to minimize the amount of stair stepping. And Solidscape actually has the best in the world when it comes to that. Our specifications and everything are down here in tooling grade accuracy and precision, and then there's other rapid prototyping machines that have a bigger market. Like if you're prototyping a toy, a kid's toy or something, you don't need jewelry kind of surface finish and accuracy and detail, and so you may use a different type of machine or technology. But our niche really is, you know, who cares about all these millimeters and thousandths of an inch or whatever, but we are down at the bottom end of the spectrum. That's our sweet spot. That's what we really excel at. For instance, if when I get called by a university who the professor is looking to buy a machine, but he's teaching mechanical engineers, and they just want crude concept models, I just say, you know what, let's not even go there. It doesn't make sense for you or I. I mean, we know where we stand, and we don't stand in that market. They're looking, you know, they got 30 students, and they want to put a little widget on a machine tonight and have a part built in an hour. That's not us. There are some competitors outside of jewelry that do very well in that type of application. Briefly, this graphic is trying to show, and we'll look at it on the individual machine over there, but we have a metal build plate to which a piece of ceramic substrate is mounted to. This all, I think you all know that it starts with designing jewelry in a computer software program. That can be Rhino, JewelCAD. There's a product now from a company called Vision Numeric out of France called 3Design. A lot of jewelers are now using that. There's Matrix from a company called Gem Vision out in Iowa. Those are the most commonly used design softwares. So those are the four main ones. Some jewelers are using old-fashioned mechanical engineering type of software. Not a lot, but there's some jewelers here in New York that are still using a product called SolidWorks. You know, that's a kind of, it's a great software. It's not easy for a jeweler to learn. Are you using it?
I'm trying. Yeah.
Oh, it's a great software. But it's the same software that they use to design Boeing airplanes. But, you know, if you can master it, I know some guys that have been using SolidWorks in the jewelry industry for 8 or 10 years, and they do beautiful work with it. But anyway, you get done with a design file in the computer, and you typically save it as in an output format called STL. The machine will also take SLC files. You bring that file into a software that comes with a machine called ModelWorks. I'm going to talk about ModelWorks software in a bit. Basically, that software is going to control our jets. But what we're doing is, again, we're building up the model layer by layer. And under every model, like if this was a model, I'm going to put a couple layers of this purple material, the dissolvable support structure. We call those platform layers. We'll put down like 2 platform layers under this case, and then it's going to start building the green stuff on top of those platform layers. So we're building the model up. The dissolvable support structure kind of throws people for a loop too, but that is intended, maybe it was some kind of piece of jewelry, maybe not, but if we didn't have the purple material under here and we're jetting from above, there would be air down here, and these droplets would all fall down to the ceramic substrate. So what we do is wherever there's holes, cavities, or undercuts, we squirt down the purple material. And That way the green material on a layer above it has something to land on instead of dropping all the way to the table. Is that kind of clear to you?
Base.
A lot of people get confused by that. I'm going to tell you how we remove that dissolvable support structure in a minute. Here is just a side view of this. It's almost like a wood planer. It's called a planer surfacer that sweeps across and mills off the little bumps on the top of each layer before the next layer starts to build. Go through a little about the machine design. Here's a close-up picture of the two jets that are mounted on the machine. Again, the green one for the build and the purplish one for the support material. This is a view looking down on the top of the machine. The jets are mounted onto this carriage assembly right here, and the carriage assembly is also tied into some flat, what's called linear bearings with a tongue and groove alignment or slot in there, so it really tightens up when you're putting down droplets that are 3/1000ths of an inch in diameter. It's very important to have good motion control because, again, that's going to affect surface finish. Here, these two caps in the back of the machine are where we put the raw material. Down inside of here are the heated tanks. The material's melted, pumped up through these black heated lines down into the jets. As I think I said, the jets also have little heater elements, so everything is molten all the way to the time it gets deposited. Under that black shroud right there is that cutter I was talking about. That debris that gets milled off gets sucked up through a vacuum hose and down into a vacuum cleaner underneath the table here. So that's a real quick overview of what the machine's all about. Here, without the covers on, is the back of the machine. It's all insulated, and there are the two heated tanks. Nothing really important on that slide. Again, one important thing that I'll touch on now, because it's a good picture of it. The jets are the only thing that we know are going to fail probably the first year you own the machine. Our average customer, from surveys we've done of those 2,000 plus jewelers, does about 30, maybe 40 models a month. That's the average. We have a lot of high volume service bureaus and high volume manufacturers that do upwards of 150 models a month with that T66 machine. On the flip side, we have some customers that do 8 or 10 models a month and own the machine. But the average is about 30 or 40 models a month. At that rate, based on our data, the jets last about 9 months before they wear out. The machines ship with a set mounted on the machine, but they are also as a spare set of jets that you can leave up on the shelf. Your operator can have them up on the shelf. But in theory, roughly about 9 months after operating this thing at the pace of 30 or 40, the jet's going to have to be replaced. And it's very easy to do, and that's why I thought I'd bring it up on this slide. There's 3 screws, one here, and one on the back side, and a little ferrule right there. And all your operator has to do is pause the machine, unscrew the 3 screws, disconnect that little ferrule. They take like a little pair of pliers, you raise up this insulation. There's a little nut under there. You just loosen the nut, take out the ferrule, pop out the old jet, put in the spare that's on the shelf, tighten down 3 screws, tighten down the nut, and you're done.
You know when it goes.
Well, you're going to actually, yeah, you're going to get some symptoms. I mean, you're going to start to see some jet errors that are displayed on the monitor here. But you can also, and then typically what happens is a guy calls the factory, our 800 number, says, I came in this morning, there's 27 jet problems from last night's build. And the guy will talk them through it. And usually what we can do is keep the jet going another couple of weeks by manually increasing the voltage that's going to those jets. So it's kind of an early indicator that this thing's about to die, and you can usually keep it going another couple of weeks.
And are they expensive after to replace them?
Yeah, I would think you're going to say they're expensive. They're $1,000 a piece. They are covered under warranty or annual service contract. And as I said, we have a spare set that ships with the machine. But what happens under warranty is after you take that old one out, You call the factory, they give you an RMA number. You ship the jet back to us, and we replace it. We overnight back a replacement jet, so you always get the spare up on the shelf. The reason we do that is, you know, it's the proverbial, somebody calls it Friday at 5 o'clock, you know, from Los Angeles into New Hampshire. Oh, I got this important job, man. I'm going to lose my customer, blah, blah, blah. So we actually just started shipping a spare set, so that can, you know, the guy can do it out in the field easily and replace it. It is the heart and soul of the machine. The reason they're expensive, they're actually made in a clean room environment. I'm not going to get too technical about it, but they're inside there is a piezoelectric crystal, which is a naturally occurring crystal that when you apply electrical voltage to it, the crystal kind of deforms. And my best analogy, it's almost like milking a cow, except the thing is like firing gazillion cycles a second. But the more voltage you put on it, the faster the thing basically squeezes. And we just found out in jewelry, it is about 8-9 months, something like that. If you're only doing 10 or 15 models a month, maybe you'll get a year and a half out of a set of jets. But that thing just basically wears out. And we have not found over the last 10 years any better device to use to do what we need to do. So that's the reason, but also these jets are kind of, like I said, made in a clean room environment. There's a lot of little potting, and they're basically hand assembled at our factory. But they are the heart and soul of the machine. We have a patent on what's called vector jetting. Why is that important with jewelry? Again, it's surface finish. There's some machines out there that kind of do the same thing ours do, that use a thing called raster-based jetting. But I'm just going to vector jetting in a nutshell means that the jets can move in the X and Y axis simultaneously. In other words, it can draw a nice smooth curve. And that's why it's important for jeweler. The rasterized jetting, you kind of get this stair-stepping effect because let's say this is one of our competitors. They've got a bunch of little nozzles mounted to an arm, a bunch of little jets. But the electronics tells, maybe let's just say there's 26 jets here. It'll tell jet number 1, 2, 7, 11, 14, you're supposed to be on, and these other guys are supposed to be off. And then a nanosecond later, you know, other ones are on and other ones are off. So the thing's going like that, and when that happens, that's when you're going to get these tessellated or stair-stepping type edges. Again, I don't want to get too technical, but that's one of the main reasons why we also have a nice smooth surface finish. We have a jet check station on the machine, which comes into play mainly at night when you're all home sleeping. There's quite a bit of self-diagnostics in this machine, but at the end of every layer, the material has to cool for a few seconds, about 8 to 10 seconds. While that's happening, the jets go over and actually shoot a line of material down onto a silver drum, and I can show it to you after when we're looking at the machine. There's a little electronics card here that's got an optical sensor on it. And what that sensor does is it's looking at the line of material being sprayed down on the silver drum. That silver drum rotates. And it's looking to see if the line is too thin, if it's too thick, or if it's shooting at an angle. If the sensor likes what it sees, it says, okay, I like what I see, you're good to go, build your next layer. If it doesn't like what it sees, too thin, too thick, or the line is crooked, it says, I don't like what I see, I want you to go over. There's you can't see it too well, but there's a roll of tape here that spools off and comes across here. It goes over, and basically the bottom of the jet wipes itself in the tape. It's kind of like wiping a runny nose. The theory is, and the reality is, that there may be a little minuscule piece of material that for some reason isn't quite melted, and it's, you know, making the thing almost like your kitchen faucet or whatever. You turn it on, the thing's shooting at an angle. I mean, the same kind of thing can happen with these jets that are shooting out 3,000th of an inch droplets. So usually it just wipes itself, it cleans itself, and then it goes back over, shoots another line on the drum, and the thing says, okay, now you're good, go back, do your next layer. So at 3 o'clock in the morning, it will do this on every single layer. If it's going to try to fix itself 5 times. If it can't, I think it's 5, maybe it's 7 times. If it can't, it will stop the machine. An error message will pop up on the monitor, And it basically means it needs some kind of human intervention, meaning when the operator gets to work the next morning. Now, this is not a frequent problem. 95% of the time it fixes itself, but it does happen on occasion. And usually the remedy is when the operator gets to work in the morning, they just have to do what we call purge the jet, which is very simple to do, and I can talk about that a little more in the future. But the important thing is you don't lose the model. It's not wrecked. It's not, you can continue the build after the operator purges the jet and just keep going. But it's actually a pretty good feature. This talks about machining every layer. I think I've talked about that enough. There is one additional benefit with this technology over some others. If there was a power failure in your building, a lot of machines like this, competitive machines, if you lose power for any reason, you lose your model. You can't recover from a power failure. This thing is smart enough that it knows, like right now, that job that I paused, it's on layer 430 out of 495, so there's 65 layers left. If I came in this morning and there was a power failure in this building, we can cut back. We know we're at layer 430. We just cut back to like layer, we use that cutter. We cut back to say layer 428. The thing's smart enough to say, okay, now I'm at 428. Resume the build, and it'll build 428, 429, and 430, and we'll be right back to where we were. And so you don't lose the model or anything like that. So that's pretty neat. We can also, interestingly enough, there's a thing in here called variable layer thickness. And it's usually only used with industrial projects. Well, anyway, I had a big, maybe Brian will come back with it. We just built a sample model for somebody in New York. It's like some big gangster rapper type piece of jewelry. It's this huge bear head. Oh, here it is. Variable layer thickness is a case, I'll let you look at it later on. But sometimes you have a model where there's not a lot of detail going on the first 100 layers or 150 layers. Well, this is a case where you could actually, in the ModelWorks software that comes with the machine, you could tell it to build the first 100 layers at the coarse resolution, like a 3/1000th of an inch. But there, when the feature detail kicks in, you can have the machine automatically go to a finer layer thickness. So that's...
I'm sorry, is there a time difference with that?
Yeah,
like
yeah, it's directly proportional to, and I'll talk about that. If an average engagement ring, let's just say one piece on this machine took 7 hours to build at 1/1000th of an inch, it would take roughly 14 hours at a 1/2,000. It's almost directly proportional. It's just a close-up of this without the black shroud, that cutter I talk about that scrolls across. You know, occasionally the operator pops off the black shroud with a ship, what we call the ship kit. There's a little brush in there that they can just brush off debris that might be stuck in the teeth, if you will, and actually you can just suck it up while you're brushing with that vacuum cleaner. Just clean it all up. You don't have to sharpen these blades or anything. They're very sharp, but again, you're only really milling or cutting something that's like a wax almost. So it's you know, the only weird thing that could happen, I guess, is if ever there is a screw vibrated loose somewhere and the cutter went over a metal screw and got a little ding on it, a little burr or something, it would probably have to be sharpened, which you can do, but it's, I don't know really of anybody that's had to do it for 7 years I've known with a company. That's really that important. Let's talk about the dissolvable support structure. This is a gross, some widget, let's call it. It's not jewelry, obviously, but it's a piece of something industrial. And inside there, you got a cavity that's got to be filled with some type of support structure. Well, the beauty of this dissolvable stuff is that there's other machines that, like, I don't know if any of you have looked at this German machine. It's called the Perfactory machine from a company called Envision Tech. they got two problems. Well, one, their material isn't cast very well, but secondly, the designer has to figure out how to support the model himself or herself. And they have to actually design in the physical supports. And the physical supports are almost like scaffolding, like you'd see out on the sidewalk. I mean, there's actual little scaffolds that hold things up.
It looks like wires.
Yes, exactly. And so there's two problems with that. One, the designer, hey, I'm a jeweler. I don't want to, you know, I love designing the jewelry on the computer, but I don't want to design it. Where am I supposed to put these supports? But anyway, they got to figure out, draw little lines or whatever in the design and figure out where to put these supports. But more importantly, when the model is done, prior to casting, somebody's got to go in there with like a little utility knife and physically cut those supports off. Well, you can see people are pushing the limits with technology and making things more delicate and fine, and there's an excellent chance that you're going to go and cut off a feature that you really wanted to be there. With our technology, here's a case of a couple of rings. You got a pave with 1,000 little holes around it. All those holes are filled with a purple material. Here, you've got a ring that when you're building it outside, you got 2 rows of prongs, so obviously this would be green. We want that to be air, so that's going to get filled in with a purple support material, and then you got another green set of prongs. But what you do, when the model comes off the machine, we ship a little hot plate with the machine. And if you remember, I said that it's a metal plate with that ceramic on top of it. And on top of the ceramic is a couple of platform layers of purple material. So I take the metal plate, I stick it on the hot plate. Within a couple of minutes, those platform layers are going to loosen up. They're going to start to melt. And then if this is my model, I can just pluck this now right off the substrate, okay, with my hands. Then I would put it in a typically a little, like a kitchen strainer basket, because we're talking about a small piece of jewelry. And I put it into a heated solution that we sell called BioAct VSO. It's really not that important, but it's almost like a refined kerosene. And we sell little 1-gallon drums. You use maybe a gallon every 2 months, something like that. But you heat that up to 55 degrees centigrade. You take the kitchen strainer with the purple goop on it, you lower it down into maybe an inch or an inch and a half worth of this heated solution, and within about 20 minutes, the purple stuff's just going to melt. Then I pull out my kitchen strainer, and I'm left with this. Put it on an paper towel, let it leach into the paper towel, let it air dry, and bingo, you're ready to put a screw on it and cast. So that's briefly how that LP waxing operation operates. As I said, some of the competitive things, you got to go in there and cut these physical supports away. If you can get to them, that's another problem. The graphical user interface software is a fancy way of defining what that ModelWorks is I was talking about. That's a software that comes with a machine. It's where you import your SolidWorks file or anybody's design file. You bring it into our software, and that's where the operator does a few things. That's where the operator will assign the layer thickness they want that job to be built at. Maybe it's a really important customer. Oh, this is an important customer. Let's build it at the finest. So today we're going to run this plate at 0.5 of an inch. Maybe tomorrow, it's, you know, Jose, he's not that picky. We'll run it at a 1.5 of an inch. So tomorrow I'll run my job at 1.5. But this, in this software, is where the operator assigns that layer configuration, we call it, or the layer thickness. It's also where the operator can virtually orient the parts in the bed of the machine, which isn't a big deal, but there's tricks of the trade, obviously. If this is the left edge of my build plate, I want to get as many models as I can over to the left side of the machine, because the whole carriage assembly doesn't have to travel as far. It's just got to go like 1 inch back, instead of going 6 inches and back. And when you're doing that 1,000 layers, 1,500 layers, although we're only talking seconds, so seconds are important. So the operator, and we cover it in training, you know, has the ability to lay out the job virtually on the computer the way they want to do it. There's some other little tricks of the trade that we go over in training, and it has to do with this orientation. We have found over the years, for instance, that it's best to face prongs towards our cutter. I'm not exactly sure why. It's just one of those things we found out. So the operator can grab that ring, if you will, rotate it 90 degrees so it's facing the cutter. There's certain geometries that we found that sometimes it's good to tilt the ring 5 or 10 degrees to get the optimum surface finish. So in software, and he's not going to do this week one, but he or she will get used to it. And now in this software, they could say, okay, I've rotated 90 degrees, plus I want to give it a 10-degree tilt. So I'll go 10 degrees, and that'll fill in support material under that 10 degrees. Long story short, that's the kind of stuff that's done in this software. The most important thing is the software is intuitive enough on its own to figure out where to put. It's going to look at your SolidWorks file and say, I know where to put that support. It does it automatically, whereas some of the other, like I said, the operator has to figure that out and design it into their design file. Here, our software says there's a gap, there's a hole, there's a cavity, there's an undercut. Boom, I'm going to put purple there, and I'm going to put the green where it should go. And so when all of that is said and done, then you save it as what we call a C6 file and send it to the machine. That's basically kind of what the process is. Just like you'd send a Word document to the printer, now when I'm done manipulating it here, I send my design file to that printer. And the printer should be networked, and if you don't have a network, our technicians or Romanov's technicians can easily help you set up a little network so it runs really well. The consumables. Number one, there's a rough rule of thumb that the consumable materials are about $2.50 per average ring, which isn't bad at all compared to some of our competition.
Now, is that including the jets or no?
It is not including the jets.
Sure.
It's a good question, though. When an owner or the CFO or controller or somebody is making a business decision, return on investment, the long-term cost of owning the machine, you should calculate in for your second, third, fourth year, either the cost of replacement jets or the annual service agreement. This is just the actual consumables, but it kind of shows you what's included. The green and the purple material, that roll of tape I talked about for the jet check station, the dewaxing solution, and this ceramic substrate that's on the build plate. Those four things in total cost about $2.50 for an average model. If you're doing like a class ring or something, that's probably $5. But if you're doing a thing, eternity band, that might only be $1.50. But again, average, it's about $2.50. So our average customer is probably spending $75 to $100 a month on consumable materials.
How much are those bottles of replacement?
That's about $163, and that's about $113. But you'll probably get 2 months or more out of a bottle. It doesn't look like it, but
no,
you're only really
you're
only talking like really a little. At the end of the day, an engagement ring probably takes like a teaspoonful of material, but yeah, you look at it, 163
So you can get like 60 pieces basically out of those 2 bottles.
Yeah,
average
roughly.
piece, about
Yeah.
60 pieces.
Yeah. Yeah, that's another way to look at it. There's some routine maintenance required. It's not difficult, but let me just talk about them quickly. We recommend at the beginning of every job, the operator calibrate the machine. And there's 2 calibrations that have to be done. One is well, let me first talk about the jet volume calibration. That's important because you don't want too much material coming out of the jets, and on the flip side, you don't want too little material coming out of the jets. So similar to calibrating some other devices, there's a little business card holder, I call it a business card holder on the machine that I can show you later, but you basically take a 3-digit gram scale. By the way, we recommend Tanita's got a little portable scale. You can get it from somebody like a Romanov or a Guess Wine or whatever usually, and they're like $230. They go out to milligrams, 3 digits. They're portable. You can keep it on the table right next to the machine. But you weigh an empty business, you put the thing on the scale, you weigh an empty business card, then you put it on the machine and you go through a menu here, calibration menu, and basically you're going to print like a 1-inch square of material. After it prints that 1-inch square, you take it off the machine, you put it back on the scale, and whatever the value that's displayed on the scale is, you type it onto the keyboard. If it's 180 milligrams, you put 180, enter. And the software is basically automatically going to calibrate the machine. So really, that's the extent of the labor. You may have to do, your operator may have to do that 1 or 2 times that morning or 3 times to get it right. I mean, if it isn't in spec, the software is going to make some adjustments and ask you to do it again. You do it, and usually the 2nd or 3rd time, boom, you're in there, and you can move on.
And you do that every time you do it?
We recommend you do it every time. The reality is, I wish people would do it, but the reality is they don't.
They don't at all?
Well, there's funny stories. Some guys, after they get it's like having their baby, right? After they get used to running their baby every day, they know that machine inside and out. And if the thing ran beautifully last night, they'll cut a corner and they won't calibrate it. Certainly you shouldn't go 3 or 4 jobs without calibrating, but I've had situations where I've gone into an owner of a jewelry company, hey, I don't know what's happening, you know, my models are great and the last 3 weeks have been terrible. The first question I always ask him is, when was the last time you calibrated the machine? Well, obviously the owner doesn't know, and he calls somebody, hey, get over here, when was the last time you calibrated this machine? The guy goes, oh, about 3 weeks ago. But it has everything to do with good model quality.
Right.
And the 2 calibrations only take about 20 minutes. And in my opinion, if you get a 24-hour build or a 22-hour build and you want the best quality, is 15 or 20 minutes worth it? I think it is. But if you think about it, well, let me talk about the positioning calibration. Positioning is basically the same kind of thing. You take a blank card, you stick it on the machine, you go into the menu, and it's going to print a card here that's like with letters across one axis and numbers up the other axis. And it's printing cross hatches of both color materials. And in an ideal world, they should overlap each other the best right smack dab in the middle, and we call it the E5 calibration. That's halfway across is E and halfway up the scale is 5. You need a loop unless your eyes are super, but anyway, you print this card, you take your loop, you kind of look around and you say, nah, it's not quite at E5, it looks to me like it's C2, where they overlap the best. So on the keyboard, I just go C2, enter. And again, the software is going to do the calibration. That's similar to like calibrating other type of printers, but what's going on there is you don't want the purple shooting onto the green, and you don't want the green shooting onto the purple, because that's going to give you a rough surface finish. So that's why calibration is important. And again, it's about a 20-minute procedure to do both calibrations. Yes, you can cheat, maybe do it every other day, something like that, after the operator gets familiar with their machine, but certainly don't go like a week without calibrating it. I talked about this. This is a dated slide. We don't recommend doing it, and I need to change this slide. But it is a cheap, low-cost way of taking the support material away. Right? Forget all the hot plate stuff. We went through that. That's the easy part. It is possible to go to Kmart and buy a $17 crock pot and use that as your dewaxing station. You would need to get like a digital thermometer, which I think costs like 70 bucks, because the temperature is important. But now what we recommended people doing, so anyway, you get your kitchen strainer basket, your crock pot, your digital thermometer, and you do what I explained before. Now we are recommending that people invest maybe I think it's about $420 for a magnetic heater stir. You can buy them from like a VWR, Scientific, or there's a Barnstead. These are companies that supply equipment to like high school laboratories and medical lab, pharmaceutical companies. But what it is, it's temperature controlled. They're good, they're precise. But they have a little hot plate type surface, and you put a little Pyrex dish or a little beaker type of thing on top of it with a magnet, a stirring magnet. And When you turn the thing on, it just slowly moves that magnet around inside the solution. It creates a little swirling action and helps accelerate the dewaxing time. So that's a recommended piece of equipment that we don't sell, that we recommend people use. However, you could do it that way. I've seen guys just take their old hot plate and put Pyrex dish on it, but the problem there is you don't get very good temperature control. And some models, again, people now in jewelry CAD/CAM are really pushing the limits with their design, and they're very delicate, and sometimes if the temperature isn't right, that purple wax is gonna, it's almost like, it's gonna be what we call, engineers call thermal expansion. That purple wax might just go